Hello and welcome back to the Deep Dive. This is a bit of a special edition we're doing today.
Yeah.
It's custom tailored for everyone. It's Simplified UPSC by PPP. And, let's just be real for a moment. The UPSC Civil Services exam.
Yeah.
It's a beast.
Oh, absolutely. It's not just about what you read.
No. It's about retention. It's about being able to hold on to this massive amount of information and then actually being able to use it when you're under that intense pressure.
That's the word right there. Use it. Deployment. You can read an NCERT textbook, 10, 15 times? But if you can't recall the specific mechanism of, say, a rift valley when you're staring down a really tricky prelims question,
Then all that reading time was for nothing.
exactly, waste it.
We're facing a retention crisis, fundamentally.
Yeah.
So our mission, our whole goal today, is to take the source material, specifically NCERT Class 11 Geography, Chapter 3, the drainage system, and kind of weave it into a narrative, something that actually sticks in your brain.
We're not just reading a chapter. We want to connect the dots.
Yes. We're not just skimming, we're going vertical.
Yeah.
We want to understand the physics of the river, the geology of the rock it's cutting through, and maybe even the logic of the examiner who's setting the paper.
And we're going to link everything, and I mean everything, back to past year questions, the PYQs. Because the exam, it leaves clues, doesn't it?
It leaves a trail of breadcrumbs.
Yeah.
And we're going to follow them.
Let's do it.
Okay, but before we jump in, before we get our feet wet, I have a humble request. We're putting a ton of effort into synthesizing all this for you. So if you find value in this, if this deep dive helps you connect those dots we were talking about, please subscribe to the Simplified UPSC by PPP channel.
It really helps. It tells the algorithm that this is useful stuff.
It does. And if you're in a position to, and I mean only if you're capable, please consider supporting the show on Patreon. It helps us keep the lights on, it keeps the research flowing, and it lets us keep bringing this, super useful content to you.
And on that note, a huge, massive shout out to all of our current supporters. You guys are the bedrock of this whole operation. We couldn't do it without you.
Absolutely. We mean that. Also, get involved. Hit that like button. Share your comments. Let us know where you're listening from, what you think. We read everything.
We do.
And for all you serious aspirants out there, listen up. There are free notes with practice PYQs available on our public Telegram channel. Go grab them.
They're a great starting point.
But if you want the full arsenal, I'm talking access to all the videos in this series all at once, plus the organized premium notes.
Which are, I have to say, a game changer.
They really are. They include detailed breakdowns, tons of extra PYQs, and even model mains answers. If you want all that, you need to join the private Telegram library. Just send a DM to the public channel and we'll get you in.
All right, that's the housekeeping done. Let's get to the geography.
Chapter 3, the drainage system. It sounds a bit dry, pun intended.
It does, but it's really not. It's actually a story about energy.
A story about energy. I like that. Unpack that for me.
Okay, think of a river not just as water flowing, but as a machine, a natural machine. And its only goal is to expend energy. It starts way up high in the mountains, right? So it has a huge amount of potential energy because of gravity.
Right, it's just waiting to fall.
Exactly. And its entire life, its whole journey, is an attempt to get to what geologists call base level.
Which is usually sea level.
Usually the sea. So every curve it makes, every gorge it carves, every single grain of sand it drops.
Yeah.
That's just the river trying to kill its own energy. It's trying to reach equilibrium.
That's a fantastic way to frame it. Okay, so let's trace this life cycle. The NCERT textbook breaks it down pretty clearly into youth, mature, and old stages. Let's start at the beginning. The youth stage. This is the river up in the mountains. High energy, super aggressive.
Right. In the youth stage, the river is basically a drill. It's not interested in widening its path. It doesn't care about going side to side. It wants to cut straight down.
Vertical erosion.
Vertical erosion is the dominant force, and that's why you get those classic V-shaped valleys. The sides are so steep because the river is just cutting down, 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 faster than weathering can wear back the sides of the valley.
Okay, and because it's drilling like this, you get some very specific features. The text mentions two I find fascinating: potholes and plunge pools. Let's start with potholes. I mean, it's amazing to think the river is almost using tools.
That is exactly what's happening. It's incredible. Picture a rocky stream. Some parts are a bit softer than others, so a small depression forms.
Okay.
The water swirls around inside that little depression, creating an eddy, a little whirlpool. Now, if there are pebbles or small boulders caught in that swirl,
The water uses them like sandpaper.
more like a grinder, it spins those pebbles around and around, and they just drill a circular hole straight down into the solid bedrock. That's a pothole.
Wow. And a plunge pool is just a supersized version of that at the bottom of a waterfall.
Precisely. The water crashes down with tremendous force, hits the bottom, and swirls, carving out this huge, deep pool. And this undercutting is actually what makes waterfalls move.
What do you mean move?
They retreat upstream over time. The plunge pool carves out the base of the waterfall, undermining the hard rock layer at the top of the lip. Eventually, that lip has no support, and it collapses. The waterfall has just taken a step backward.
So the waterfall is slowly eating its way back into the mountain.
Over millennia, yes.
Okay, now, in this youth stage, there are two terms that I think a lot of people, myself included, sometimes use interchangeably, but geologically they're very different. Gorge and canyon. To the average person, they're just big, deep holes in the ground. What's the real difference?
It all comes down to the type of rock and the pattern of erosion. A gorge. Think of a gorge as a slit. A deep slit cut into the earth. It has very, very steep, almost vertical sides.
Like a knife cut.
Perfect analogy. And crucially, a gorge is almost the same width at the top as it is at the bottom. It doesn't really flare out.
Okay, so it's like a vertical slice.
No. Yes. The NCERT gives a great example. The Kaveri River near Hoganikal. It's cutting through really hard, resistant rock. The rock is so tough that it doesn't crumble and form a slope. It just holds that vertical face as the river cuts down.
Right. Now let's contrast that with a canyon. And of course, the image that comes to mind is the Grand Canyon.
The classic example. A canyon is usually much wider at the top than it is at the bottom, and this is the key visual clue. It often has step-like slopes.
Step-like a staircase.
Exactly like a staircase. This happens because canyons typically form in horizontally bedded sedimentary rocks. So you've got these layers stacked up like a cake. A layer of hard rock, then a layer of soft rock, hard rock, soft rock.
And they wear away at different speeds.
Precisely. The softer layers of rock erode back much faster, creating a gentle slope. But the hard, resistant layers hold firm, creating a vertical cliff. You repeat that pattern 100 times down the valley wall, and you get these giant steps.
So to simplify it for an exam answer, gorge equals hard, uniform rock, leading to vertical walls.
Yeah.
Canyon equals layered, sedimentary rock, leading to stepped walls.
That's a perfect summary. A great visual distinction to hold in your head.
Okay, there's one more feature in this youth stage that always seems a bit contradictory to me. Incised meanders. When I think of meanders, you know those winding snake-like curves? I picture a slow, lazy river on a flat plain.
Right, the old stage.
Exactly. But the text talks about these deep meanders cut into hard rock mountains. How does that happen?
This is a favorite concept for geologists because it tells such a fantastic story about time and change. You're absolutely right. A river shouldn't naturally start meandering in hard rock. It just takes way too much energy. So if you see a deep, winding canyon, it's what we call an incised or entrenched meander.
So how to get there? It feels like a geological puzzle.
Think of it like this. Go back millions of years. Imagine a river flowing across a flat, soft plain. It's in its mature or old stage, so it's meandering lazily, swinging from side to side.
Okay, I'm with you. A normal meander.
Now imagine that powerful tectonic forces start pushing that entire plain upwards. The land itself starts to rise.
Like the whole landscape is on an elevator going up.
A very, very slow elevator, yes. But the river is still flowing, right? It has to go somewhere. So as the land pushes up beneath it, the river acts like a saw. It has to cut down just to maintain its level to keep flowing.
So it's not creating the meander pattern in the hard rock.
No, it's preserving a pattern that was already there. It incises its old meandering path right into the rising bedrock. So when you stand at the edge of an incised meander today, you're literally looking at a fossilized behavior. The river isn't choosing to meander there now. It's stuck in the path it chose millions of years ago when the ground was flat and soft.
That is a brilliant analogy. The river is the saw, and the earth is the log being pushed into it. Wow. Okay, let's follow the river downstream. It's leaving the mountains. It enters the mature stage.
The energy level starts to drop, the aggression settles down a bit. The river is now entering the foothills, maybe the upper plains, and here it starts to create wider floodplains. The V shape of the valley begins to broaden out.
And waterfalls.
The waterfalls and rapids are gone. The river has graded its profile. It has smoothed out the bumps in its path.
And finally, it reaches the old stage.
Mm.
The river is, what, tired?
Tired is a good word for it. It's barely moving. The gradient is so gentle you can hardly see it. Now the river is flowing over its own deposits, the silt and sand it has carried for hundreds of miles.
So it's no longer eroding downwards.
Not really. The main action is deposition. It's just trying to carry its remaining load to the sea. And this is the landscape where we see those vast floodplains, the natural levees, and the famous Oxbow lakes.
That's a perfect transition. Let's do a deep dive into these depositional landforms in segment 2. The river is now a builder, not a destroyer. I want to start by contrasting two major features that can look similar from above: alluvial fans and deltas.
A great comparison. Both look like a fan or a triangle, but they form in completely different environments and through different processes.
Let's start with the alluvial fan.
Okay, for an alluvial fan, I want you to picture a dump truck. A stream is rushing down a steep mountain valley, carrying a huge, messy, load-heavy boulders, gravel, sand, everything. Then, suddenly, it hits the flat plain at the foot of the mountain. Its velocity just crashes to almost zero, instantly.
So it panics and just drops everything it's carrying.
Exactly. It dumps the entire load right there in a big cone-shaped pile. And because it all happens so fast, the material is completely unsorted. You'll find giant rocks mixed in with fine sand. It's a chaotic jumble.
Right, a messy pile. Now compare that to a delta.
A delta forms at the complete other end of the river's journey, where it meets the sea or a large lake, and this is a much slower, more delicate process. If the alluvial fan is a dump truck, think of a delta as a meticulous sieve or a filter.
A sieve, okay. How so?
As the river flows into the standing water of the sea, it slows down gradually, not all at once.
So it has time to sort the material it's carrying.
It has time to sort it perfectly. The heaviest, coarsest material, the sand and gravel, settles first, right near the shore. The finer silt gets carried a bit further out, and the very finest clay particles, which can stay suspended for a long time, float out even deeper into the sea before they settle.
So it's stratified, layered, and well sorted.
Exactly. The visual to keep in your mind is that satellite view of the Krishna River Delta mentioned in the source material. It's a highly structured, organized extension of land, not the chaotic pile you see in an alluvial fan.
Okay, that's a very clear distinction. Speaking of structure, let's talk about levees. The text mentions natural levees. I think most of us picture levees as these big concrete walls built by engineers to stop floods. How does a river build its own wall?
It's a fantastic process, and it's all about flood dynamics. Imagine a river flowing within its channel. Then a big flood happens, and the water overflows its banks and spreads out across the floodplain. The very moment that water leaves the deep, fast-flowing channel and hits the shallow, flat floodplain, it slows down dramatically because of friction with the ground.
And as we just established, when velocity drops, sediment drops.
Correct. And what does it drop first?
The heaviest stuff.
The heaviest stuff. And it drops it right on the edge of the bank. So with every single flood year after year, another thin layer of coarse sediment gets deposited right along the river's banks. Over time, the river builds up these low, linear ridges on either side of its channel. Those are natural levees.
That's fascinating. So the river actually contains itself over time. Now, what about inside the channel? Let's talk about point bars.
Point bars are the mirror image of erosion in a meander. On a winding river, the water doesn't flow at the same speed everywhere in the channel.
Explain the physics of that. Why is it different from the inside of the curve to the outside?
It's all about centrifugal force. It's the same reason you feel pushed to the outside when you go around a corner in a car. The water does the same thing. It piles up on the outside bank of the curve. That's the concave bank.
Okay, so more water on the outside, moving faster.
Moving faster and with more force. So it erodes that bank, cutting it away. It's called a cut bank.
And on the inside of the curve?
The convex side is sheltered. It's the slow lane. The water moves much more slowly there. So what does it do?
It drops sediment.
It drops sediment. And these deposits on the inside of the curve build up to form a point bar. So over time, you have this constant push and pull. The outside bank gets eaten away and the inside bank gets built up.
And that's what makes the meander loop get more and more exaggerated.
Yes, the loop gets tighter and more sinuous.
Until, eventually, the loop is so tight that the river just decides to take a shortcut.
Exactly. During a big flood, the water has so much energy, it just punches straight through the narrow neck of land separating the two ends of the loop. It takes the shorter, steeper path.
An old loop is just abandoned.
It's cut off from the main flow. It becomes a stagnant, crescent-shaped lake. An oxbow lake.
The NCERT points to the Buhi Gandak River near Muzaffarpur in Bihar as a prime example of this. You can see the scars of old meanders all over the floodplain. But here's a question. What's the fate of an Oxbow lake? Does it just stay there forever?
No, it's a dying feature. It's a transient part of the landscape. Since the main river no longer flows through it or feeds it with fresh water and sediment, it starts to fill in.
With what?
With silt from the occasional flood that might still reach it, and with decaying vegetation reeds, water lilies, things like that, it slowly turns into a swamp or a marshy wetland, and then eventually it can dry up completely and just become a curved scar on the floodplain.
A ghost of the river's path.
A perfect way to put it.
Okay, one last depositional feature before we switch gears. Braided channels. I've seen those satellite photos of the Brahmaputra, and it's just mind-boggling. It looks like a tangled mess of silver threads. Why doesn't it just flow in one single big channel?
For a braided channel, the best analogy is a massive traffic jam on a highway where there are obstacles everywhere and everyone is trying to find a way through.
So what causes the traffic jam?
A massive sediment load combined with a variable discharge, or flow of water.
So the river has too much luggage, too much baggage to carry effectively.
Precisely. The Brahmaputra carries a colossal amount of sand and silt from the Himalayas. When the water level drops slightly, say after the peak monsoon melt, the river just doesn't have the energy to carry all that sand anymore.
So it drops it.
It dumps it right in the middle of its own channel. This forms a central bar, an island of sand. The water is then forced to split and flow around this bar in two or more smaller threads. Then those threads might rejoin downstream, only to split again when they encounter the next sandbar.
And you get this complex, interwoven pattern.
It's a sign of a very high-energy environment with an overwhelming amount of sediment. It's classic for rivers coming out of young, rapidly eroding mountains like the Himalayas.
That transitions us perfectly.
Yeah.
Segment 3, the clash of the titans, the Himalayan drainage versus the peninsular drainage. This is, as you said, the high-yield zone for the UPSC exam.
Absolutely. This is where the examiners love to play. They want to see if you understand the fundamental differences in how these two massive river systems evolved.
Okay, so let's start with a concept that the NCERT mentions, but I think a lot of students just gloss over it. The idea of antecedent drainage. What on earth does that mean?
It's a fantastic concept. Ante means before. Cedent means to go. So these are rivers that existed before the landscape they flow through was fully formed.
Wait, unpack
What?
that. The river was there before the mountain. That sounds impossible.
It sounds counterintuitive, but it's true for some of our biggest rivers. The Indus, the Satluj, the Brahmaputra, even the Kosi. These rivers are geologically older than the Himalayas themselves.
How does it even work?
Okay, picture the scene about 50 million years ago. There's a river flowing across a relatively flat plain where the Himalayas are now. Then the Indian plate starts crashing into the Eurasian plate, and the Himalayas begin to rise.
The mountains are being pushed up from below.
Right. They're rising maybe a few millimeters a year. A powerful established river doesn't just stop or flow around this slow uplift. It maintains its path. It just keeps cutting down as the mountain rises beneath it.
So it's the saw analogy again. The river is the saw, and the mountain is the log being pushed up into it.
Exactly. It saws its way through the rising Himalayas, and that is why these mighty rivers flow through incredibly deep, narrow gorges right through the highest parts of the mountain range. They didn't find a gap in the mountains. They made the gap while the mountain was growing around them. That is the definition of antecedent drainage.
That one concept explains so much about the geography of the North. Incredible. Now let's pivot south. The peninsular rivers. They're much older, flowing over a more stable landscape, but there's a huge anomaly here, something that was the subject of a really tricky 2013 prelims question.
The west-flowing rivers.
Exactly. If you look at a relief map of the Deccan Plateau, the whole thing has a general slope from west to east. That's why the big rivers, the Godavari, the Krishna, the Kaveri, all flow east and drain into the Bay of Bengal.
Makes sense. Water flows downhill.
Right. But then you have the Narmada and the Tapi, and they flow west into the Arabian Sea against the general tilt of the plateau. The 2013 question asked why.
This is a classic trap question. Let's think about the probable options that would be in a student's head. Option A might be, it flows in a linear rift valley.
Okay.
Option B could be, it flows between the Vindhya and Satpura mountain ranges. And option C, the tempting one, might be, the land slopes to the west from central India.
I have to admit, option C sounds really intuitive. The land slopes to the west. Simple. Water flows downhill.
Yeah.
A lot of people would probably pick that.
They would, and they would be wrong. It sounds logical, but it's geologically incorrect as the primary reason. The Narmada flows west because it is trapped in a rift valley.
Explain what a rift valley is.
A rift valley is a type of fault block. The Earth's crust in that region cracked, and a long, linear section of land dropped down between two fault lines, forming a trough or a valley. The Narmada River is confined to this trough.
So the local slope of the valley floor overrides the general slope of the entire plateau.
Precisely. The floor of that specific rift happens to tilt westward, so the river has no choice but to follow it.
And what about option B, that it flows between the Vindhyas and Satpuras?
That's a true statement. It does. But it's a description of its location, not the cause of its flow direction. The Vindhyas and Satpuras are the high ground on either side of the rift. They are there because the valley dropped down between them. The Rift Valley is the fundamental causal geological mechanism. You have to choose the geology, not just the geography.
That's the level of nuance UPSC is looking for.
Right.
It's not just what, but why. Okay, sticking with the West Coast, another great question from Maine's 2013. There is no formation of deltas by rivers of the Western Ghats. Why?
This question connects right back to our dump truck versus sieve analogy we discussed earlier. To build a delta, a river needs a few key ingredients.
What are they?
One, it needs a long, gentle course to have enough time to grind down rocks into fine silt and clay. Two, it helps if it flows over softer rocks that erode easily so it can pick up a lot of sediment. And three, it needs a gentle slope where it enters the sea so it can slow down and deposit that sediment.
And the rivers flowing west from the Western Ghats?
They have none of those things. Rivers like the Periyar in Kerala or the Shiravati in Karnataka are incredibly short and steep. They basically just fall off the edge of the Western Ghats.
So they flow very fast.
Very fast. And they flow over some of the oldest, hardest rocks on the planet, so they don't carry much sediment to begin with. And when they hit the Arabian Sea, they are still moving so fast that they just dump whatever little sediment they have into the deep water. There's no time or space to build a delta.
So they form estuaries instead.
Correct. An estuary is just a drowned river mouth, a funnel-shaped inlet where the fresh water of the river meets the salt water and tides of the sea. No new land is being built.
Okay, let's switch from land building to land destroying. Disasters, landslides. This was another comparison question from Maine's 2013. Bring out the causes for more frequent occurrence of landslides in the Himalayas than in the Western Ghats.
This is a beautiful question because it forces you to compare the fundamental character, the skeleton, of these two mountain ranges.
Let's start with the Himalayas.
The Himalayas are young fold mountains. Geologically, they are teenagers. They're still growing. They're tectonically active, which means they are prone to earthquakes.
They're shaking.
They're constantly shaking. And they're made of relatively soft, sedimentary rocks and, in many places, unconsolidated glacial deposits. They are, in essence, giant, steep piles of loose rubble.
So shaking ground plus loose dirt equals a high risk of landslides.
It's a recipe for disaster. It's a structural instability that's built into their very nature. Now, contrast that with the Western Ghats.
They're much older.
They're ancient. They are a stable block, part of the old Gondwana landmass. They are made of hard, crystalline, volcanic, or metamorphic rocks. Tectonically, they're very stable, very quiet.
But the question implies that landslides do still happen in the Western Ghats. I mean, we hear about them in Kerala and Maharashtra all the time during the monsoon, so why do they happen there?
And that's the brilliant twist in the question. In the Western Ghats, the primary cause isn't usually tectonic instability. It's the deadly combination of extremely steep slopes and incredibly intense rainfall.
The monsoon.
Monsoon. The western side of the Ghats has these sheer vertical cliffs called escarpments. When the monsoon hits, a massive amount of water can fall in just a few hours. This completely saturates the thin soil cover, it lubricates the joints in the rocks, reduces friction, and then gravity just takes over, pulling huge amounts of debris down the slope.
So it's a weather-driven or meteorological landslide in the Western Ghats versus a geology-driven or tectonic landslide in the Himalayas.
That distinction is the absolute key to writing a high-scoring answer for that question. Tectonic versus meteorological triggers.
Brilliant. Okay, let's shift to segment 4. This is about systems, glaciers, and what I like to call mental mapping. We need to be able to see the map in our heads now. Let's start with the Brahmaputra system. What a traveler.
It really is. It starts near the sacred Mansarovar Lake in Tibet, where it's called the Sangpo. And for hundreds of kilometers, it flows east, running parallel to the main Himalayan range.
But then it does something dramatic. If you look at the map, on the far eastern edge of India, near the peak of Namcha.
It takes a sudden hairpin U-turn and plunges south into India.
That U-turn is famous. It has
Yeah.
a specific geological name, right? A syntaxial bend.
Yes. The geology of the collision zone forces the river to bend sharply around the anchor point of the eastern end of the mountain range. It enters Arunachal Pradesh, where its name changes to this Xiang.
And it's not even the Brahmaputra yet.
Not yet. The Dibang and the Lohit, two major tributaries, join it from the eastern hills, and only after that confluence does it become the wide, braided Brahmaputra that we know in the Assam Valley.
Speaking of tributaries, there was a prelims question in 2016 asking to identify tributaries of the Brahmaputra. The options given were Dibang, Kameng, and Lohit.
And the correct answer was all three of them. But just memorizing the names isn't enough. The mental map is crucial here. You need to be able to visualize the Kameng joining from the right bank, from the north, and the Lohit and Dibang coming in from the left bank, from the east.
This brings us to another map-based question from the 2014 prelims. This one focused on Arunachal Pradesh. It asked which of the following rivers flow through the state: Barak, Lohit, and Subansiri.
This was a brilliant trap for anyone who just memorized lists without looking at a map.
Okay, break it down for us. Lohit and Subansiri.
Definitely in Arunachal. The Lohit we just mentioned. The Subansiri is another massive tributary that comes down from Tibet and flows through the middle of the state. But the Barak River...
Where's the Barak?
The Barak River rises in the hills of Manipur. It flows south through Mizoram, and then it turns north into the Barak Valley of Assam before entering Bangladesh to become the Surma and later the Meghna River system.
So it's geographically isolated from Arunachal.
Completely. It's separated by the Patkai Bum Hills and the entire state of Nagaland. If you can visualize that map of northeast India, you know instantly that the Barak is way too far south to be in Arunachal.
It proves the point. Map work is absolutely non-negotiable for prelims. Okay, let's head up into the ice. Glaciers. The 2019 prelims had one of those matching questions. Let's go through the pairs and verify them.
All right, let's do a quick fact check. Bandar Punch Glacier matched with the Yamuna.
Correct. The Yamunotri Glacier is on the Bandar Punch Massif.
Bora Shigri Glacier with the Chenab.
Also correct. It's one of the largest glaciers in the region, feeding the Chandra River, which becomes the Chenab.
Siachen Glacier with the Nubra River.
Correct. The Nubra Valley is fed by the Siachen.
Zimu Glacier with the Manas River.
That one's tricky. The Zimu Glacier in Sikkim is the source of the Pista River, not the Manas. The Manas originates in Tibet. So that pair is incorrect.
Good catch. Now, there was another pair in that question that caused a lot of confusion, Milam and Mandakini.
Right. The question presented the pair Milam-Mandakini. Is that correct?
No, it is incorrect. The Mandakini River, which flows past Kedarnath, originates from the Torabari Glacier. The Milam Glacier, which is further east in Uttarakhand, is actually the source of the Ganga River, which is a tributary of the Kali or Sarda system.
That is a very deep cut.
Yeah.
But it shows that knowing why an answer is wrong is just as important as knowing the right one. And while we're on sources, let's clarify the Ganga. It's not just one single stream from one glacier.
No, absolutely not. The Ganga is a marriage of two mighty rivers. The Bhagirathi is the one that starts at the Gangotri Glacier, specifically from the snout called Gamuk.
And the other partner?
The Alakananda, which starts at the Setapanth Glacier near Badrinath. These two rivers flow separately for a long distance, carving their own valleys until they finally meet at the holy town of Divprayag.
And that confluence is the true birth of the river Ganga.
That's where it officially begins.
Beautiful. Now let's transition from the physical river to the human impact. Segment 5, Water Resources, Management, and Crisis. This is where we bridge physical geography with human and economic geography.
And this is where the story, frankly, gets a bit tragic. We've just spent all this time describing India as this land of massive, high-energy, glacier-fed rivers, and yet we are one of the most water-stressed countries in the world.
It's a massive paradox. So let's throw the water we can't see, groundwater.
Yeah.
A 2020 prelims question touched on this.
And the fact behind that question is just startling. India has the largest area under groundwater irrigation in the entire world.
The largest.
By a huge margin. We pump more groundwater annually than China and the United States combined.
Why? What drove this?
In a word, the Green Revolution. In the 1960s and 70s, to achieve food security, we aggressively promoted high-yielding varieties of crops, like rice and wheat, especially in states like Punjab and Haryana. The problem is, these crops are incredibly thirsty, And Punjab is a semi-arid state. It just doesn't get enough natural rainfall to grow that much rice.
So we drilled.
We drilled hundreds of thousands of tube wells, and for decades the government provided free or heavily subsidized electricity to farmers to run the pumps. The result is a disaster. The Central Groundwater Authority, the CGWA, has classified a huge percentage of districts in these states as overexploited or critical.
We're mining fossil water.
We're mining it, we're pumping it out of the aquifers far faster than the monsoon can replenish it. It is a ticking time bomb for our food security.
And what about the visible water, the pollution in the rivers? You know, you'd think a river as big as the Ganga could clean itself.
And it can, to an extent. Rivers have a natural self-purification capacity. If you dump a little bit of organic waste, the bacteria in the water and the ultraviolet rays from the sun will break it down. The river recovers. But we have completely overwhelmed that natural system.
The 2013 mains had a question about the national water policy and river pollution. And then a 2019 prelims question got really specific, asking about chemicals like carbofuran and phorate.
Right, those are pesticides. The question asked why their use is viewed with such apprehension. And the reason is, unlike organic waste, they don't break down easily. They persist in the environment. They run off from the agricultural fields into the rivers, they get into the water table, they enter the food chain, and they accumulate in the bodies of fish, birds, and humans.
So they are bioindicators of how our agricultural success is systematically poisoning our own drainage systems.
A very grim reality.
Nature's own solution to this filtration problem is, of course, wetlands.
They're called the kidneys of the landscape for a reason. Wetlands are incredible ecosystems. They filter pollutants from the water, they recharge groundwater, and they act as natural sponges to control floods. Protecting them is critical, which is why we have the Ramsar Convention.
A 2014 PYQ tested knowledge on this with another matching question, pairing specific wetlands with the rivers they're associated with. This is another one for the mental map. Let's start with Harike.
Harike Wetlands in Punjab. This is a very specific, verified location. It is located precisely at the confluence of the Bees and the Satluj rivers.
Okay, that one's solid. What about the next one? Keeladeo National Park.
In Ferozpur, Rajasthan. The question paired it with the confluence of the Banas and Chambal. Now, this is where it gets tricky. Keeladeo is actually an artificial, man-managed wetland. It's historically fed by the Gambhir and Banga rivers. It is not located directly at the confluence of the much larger Banas and Chambal, so that's an incorrect pairing.
A very nuanced distinction. And the third one, Kalaru Lake.
Kalaru Lake in Andhra Pradesh. The question paired it with the confluence of the Musi and Krishna. This is also incorrect. Kalaru is a large freshwater lake that is located between the deltas of the Godavari and the Krishna rivers. It acts as a natural flood-balancing reservoir for them, but it's not at the confluence of the Musi and Krishna. The Musi joins the Krishna much further upstream.
So in that 2014 question, the Harike pairing was the only slam dunk correct answer.
It was. It shows you need precise knowledge, not just a vague idea of the region. That detail Harike equals Bees plus Satluj is something you just have to lock away in your memory.
Okay, to wrap up the physical geography, let's briefly touch on segment 6, the outliers, the landforms of deserts and coasts.
Right. In the desert, we often think of wind as the main force, creating dunes and mushroom rocks. But water, when it does arrive in flash floods, is an incredibly powerful shaper of the desert landscape.
How so?
When a torrential rainstorm hits a desert mountain range, the runoff erodes the mountain front very rapidly. Over time, the mountain front retreats, leaving behind a gently sloping, rock-cut surface at its foot. This is called a pediment.
And the vast, featureless plain that's left behind as multiple mountains retreat.
That's called a pedoplain. And where all the water from the flash flood collects in the low point of the basin, you get these shallow, temporary lakes. As the water evaporates, it leaves behind layers of salt. These are called playas.
Right. And finally, the coasts. A simple east versus west comparison.
The simplest way to remember it is this. The west coast is a submerged coast. The land has dipped down relative to the sea. That's why it's narrow, rocky, with steep cliffs falling into the sea, and why it has excellent deep natural harbors like Mumbai and Marmago. It's an erosional coast.
And the east coast.
The east coast is an emerging coast. The land is gently sloping up out of the sea, or, more accurately, it's being built outwards by the rivers. This is the depositional coast. This is where you find the massive deltas of the Mahanadi, Godavari, Krishna, and Kaveri, and long, wide, sandy beaches.
So west equals submerged, rocky, erosional. East equals emergent, deltaic, depositional.
A perfect summary.
Got it. Wow. We have covered a massive amount of ground today. I mean, from the tectonic forces birthing the Himalayas to the microscopic sorting of silt particles in a delta.
We've tried to synthesize the physics, the geology, and the human policy all into one narrative.
So let's wrap this up with our mains provocation. This is the final thought we want to leave you, the listener, to chew on. In 2015, the UPSC mains exam asked this question. India is well endowed with freshwater resources. Critically examine why it still suffers from water scarcity.
It is the ultimate paradox of Indian geography, isn't it? We are the land of the Ganga and the Brahmaputra. We have the monsoon, one of the most powerful weather systems on Earth. We have glaciers storing fresh water in the Himalayas. By all physical geography standards, we should be a water surplus nation.
But we're not. Far from it.
We're not. And the answer to that question isn't in Chapter 3 of the physical geography textbook. The answer is in management. It's about the massive spatial unevenness. Cherrapunji floods, while a place a few hundred kilometers away in the rain shadow is in drought.
It's about timing.
Exactly. The temporal unevenness. We get 80% of our rain in 3 months, leading to floods, and then we have 8 months of dryness. But mostly, at the end of the day, it's about our own inefficiency and pollution. We waste so much of the water we have through inefficient irrigation, and we poison what remains.
That is the bridge that you need to build in your mains answer. You can't just describe the rivers and the rainfall. You have to critically examine the management of those resources.
Exactly. Knowledge of the physical system is the foundation, but the application to the human crisis is where you score the marks.
We really hope this deep dive has given you that structural skeleton to hang all these facts on. Remember, don't just memorize Narmada flows west. Ask why. Ask about the Rift Valley.
Visualize the saw cutting the log. Visualize the dump truck versus the sieve. Make these concepts your own.
Before we sign off, just one final reminder. This deep dive was brought to you by Simplified UPSC by PPP. If this audio helped you today, please take a second and subscribe to the channel. It really, really helps us out.
And if you have the means, do check out the Patreon. Your support is what allows us to dedicate the time to do this deep research and produce these for you.
And for those premium notes, the detailed ones with the model answers to those mains questions we just discussed, you know what to do. Join the private Telegram library. Just DM us on the public channel to get access.
Keep learning, keep questioning, and most importantly, keep connecting the dots.
We'll see you in the next deep dive.
Goodbye, everyone.